use Splunk. It could be anything from cybersecurity use cases and or IT. But one of the things that we're aware of when it comes to Splunk, some of the challenges has to deal with around customers complain about cost of Splunk. We all know that that's not uncommon, and that has a lot to do with how we ingest data, how we index the data, and how we store the data. And so a lot of times customers are they come to us and they're looking for a lower cost storage option, but they don't want to lose sight and visibility into the data that is needed for investigations. So we know a lot of times, like over the course of the past few years, a few things that I've worked on as it relates to AWS integrations was federated search for S3. So customers that want to take their data and then instead of storing it in Splunk, they can store it in S3. And then through Splunk, you can do a federated search and search the data in S3. Or we also did another integration with Amazon Security Lake that would allow you to search the data in Security Lake. But a lot of times, depending on the type of investigation you're doing, you might want to have access more readily or quickly to that data. And so instead of going in and doing a search against the data in S3, that could take some period of time to retrieve. So Splunk we accepted the problem. We heard from customers that this is a problem. So we're looking at today of how customers are, number one, ingesting data into Splunk, how they use our Splunk base to basically download add-ons for all these various different technologies to basically then feed the data, the logs, the events, the alerts from these various different data sources into Splunk. Some customers are using tools like Cribble, other data pipeline management tools. Splunk has our own pipeline tool that we call Edge Processor, which is utilizing Iceberg, which Paul will talk about. So when customers are looking at data coming in and they're saying, well, hey, I don't want to necessarily send I want to send my high fidelity data into Splunk, but maybe my low medium fidelity data, I would rather send that to some sort of Lakehouse, and maybe the low medium fidelity, send it into like like an S3 bucket. So, prime example, VPC flow logs. A lot of customers we work with, they don't want to send VPC flow logs into Splunk. High volume, low fidelity. When I need it for an investigation. But other than that, it's just usually not a use case that we hear from a lot of our large customers that they want to send that data into Splunk. They'll send it into, like I said, something more like a cloud storage S3 or route it. Where if I'm looking at things like CloudTrail, if I'm looking at things like guard duty events, things like that, then those are the types of things that I do want to route into Splunk. So one of the things that we came up with was a storage option called the Machine Data Lake. And Machine Data Lake, when you think about Splunk, Splunk is more about, let's call it hot storage. The data comes in, the data gets indexed, I'm able to search that data in a rapid amount of time. That's the power of Splunk. That's why customers buy Splunk. But then, again, going back to that high volume data, where customers want access to it, but they want access to it in a timely manner, we came up with what we call Machine Data Lake. And Machine Data Lake, think of it as kind of more like a lower cost storage options that for customers that want to store, again, that high volume data like VPC flow logs, but without incurring the cost of it. So Machine Data Lake, again, is a kind of a cold storage option that is using Iceberg. Paul, do you want to talk about the technical parts of this?
Yeah, sure. Thank you, Colin. Yeah, so you probably all heard about like medallion data models, and right. So in a certain sense, the machine data lake follows that pattern, with some exceptions. So the landing zone of the machine data lake is really literally the raw data in its unstructured form. Where Iceberg comes into play is what we call the promotion process. I mean, we use that term. We actually overuse that term. It means so many different things. But I think for this audience, what it means is selectively taking data that's in some raw, unstructured form, which is where Splunk kind of got its reputation. You just kind of a garbage disposal. Just send us data unstructured. We'll figure it out later, often at read time. That doesn't always work well for security use cases where we need, first, some kind of normalized form of the data. So I'll give you a pitch for the industry. The Open Cybersecurity Schema Framework, for example, is a normalized form of cybersecurity data that the machine data lake can promote the data into. So the promotion process really involves a well-known schema. It involves, usually in our case, Parquet encoding, columnar-based encoding, and Iceberg for the table format. We don't do anything fancy. To be frank, we're using the Iceberg Ice APIs of Amazon. We're using the glue table to manage the tables. So nothing special there. But the customer will, and with some AI assistance, will choose what data should be promoted, because we won't promote everything. So not everything will be tabular, not everything will be schematized. And then we have one other concept we call acceleration. And accelerate, so we use a Spark-based EMR serverless approach to do the queries. And then we use a Golang Iceberg library to actually send the data in ready for Iceberg. So that bypasses the landing zone and says data that's in stream that he showed you in that path can go through. We're not super thrilled with the Go Iceberg implementation. It's not as powerful as the Python or the Java ones, but because our stream processing is written in Golang, we've used it. And so in the use cases where a customer creates a pipeline and says, I want the destination to be in Parquet Iceberg, as an example, the new CloudWatch Unified Data Store is one of those. That's how we do it. If the data goes straight into an S3 bucket, then we use the promotion process, and that isn't in real time usually. That's a step after the landing zone. The one thing people probably may or may not know, Splunk is not actually expensive to store data. We actually use S3 in our cloud implementation. The Splunk journal files are in S3, in objects in an S3 bucket. However, what we call the index files, the time series indexes, those sit on the indexers, of which there's many. And a large implementation might have hundreds of indexers. These are really EC2 instances that are using up a lot of compute time. So when people say Splunk's expensive, it is because we're indexing everything as we receive it, assuming that you're going to want to search it later. Very good at high cardinality searches, not so good for low cardinality searches. Again, that's where promoting into an Iceberg table format, where we can cross-correlate across different data sources using OCSF or a customer's bring your own schema managed by the Glue catalog, is a way for us to now kind of have our cake and eat it too. So, we're not doing anything fancy. We're using the Amazon EMR implementations. We're using the Glue catalogs I mentioned. And again, the one thing we're a little bit, less than thrilled with is the Go Iceberg libraries. But hopefully that can improve over time. I don't know if anybody else in the room has any experience with that library or not. I saw a couple people when I mentioned it sort of like, yeah, so maybe we're not the only ones that find it maybe lacking a little bit. But hopefully the open source community will improve that. I'll throw a pitch for the OCSF work. I'm a co-founder of it with Amazon. tomorrow morning, there's a breakfast. You get a free breakfast at the Intercontinental. We are a Linux Foundation project, and coming in June, we will be an International Telecommunications Union international standard. So from the standpoint of what kind of schema to use with Iceberg, we're recommending, at least for security data, we follow the standards. It's open source also. So again, Iceberg open source, OCSF open source, Parquet open source. This is just our implementation.
Yeah, and AWS, as you know, is they're a big supporter of OCSF. So just to kind of wrap it up, I'm just going to play this really quick video, just to kind of
Today, I'm going to show you how Machine Data Lake, a core component of Cisco Data Fabric, removes a painful choice security teams have lived with for years. As machine data volumes grow, teams often push high-volume telemetry like DNS out of Splunk into external storage to control cost. That data is inexpensive to store, but once it leaves Splunk, it leaves the analyst's core investigation experience. Access takes extra steps. Correlation slows down. Activation adds friction when time matters most. Machine Data Lake removes that friction by keeping all data inside Splunk, cost-effective to retain, governed, and immediately discoverable. So analysts activate and use data when questions arise, not months earlier. In Machine Data Lake, high-volume telemetry lands in low-cost object storage managed by Splunk. It's cataloged and governed automatically, but not activated for high-performance analysis up front.
This is our
Teams land
process,
everything once and
well,
activate
let's talk
only
about our
what
data
proves
pipeline
valuable.
management tool, if you're familiar
Meet
with Groeneveld.
Jason, a senior SOC analyst working in Cisco AI Canvas. He receives an alert showing suspicious login attempts into an internal HR system from a single host. His question is simple. Is this credential misuse or something more serious like data exfiltration? Jason asks AI Canvas to analyze authentication and firewall activity. Canvas flags anomalies and highlights what's missing. DNS activity would confirm whether the host contacted malicious infrastructure. AI Canvas tells Jason the DNS data already exists in Splunk. It's retained in Machine Data Lake, governed, discoverable, and ready, but not yet activated for investigation. Jason moves from AI Canvas into the catalog and promotes exactly what matters.
Paul was
This
referring
host
to.
and a 2-week window.
And then
During
promote.
promotion, he prepares the data by masking sensitive fields, normalizing host identifiers, and tagging suspicious hosts. This creates a curated data set purpose-built for this investigation. Splunk runs the promotion in the background and notifies Jason when it's ready. The curated DNS dataset appears in the catalog, optimized for investigation and AI reasoning. Jason returns to AI Canvas and asks it to reassess using the curated DNS data. Because the dataset was intentionally prepared, with normalized fields and suspicious host tags, AI Canvas immediately correlates authentication, firewall, and DNS activity. The answer is clear. The host contacted a known malicious domain shortly after the suspicious logins. This is the difference. Machine Data Lake keeps data cost-effective until value is proven, and AI Canvas turns that data into answers.
Very good, thanks.
Yeah.
Well, one last point. The Iceberg support extends beyond Machine Data Lake. We can also support external data lakehouses if you are using Iceberg. So our stream processor can normalize, can encode to Parquet, and then can set with that Go Iceberg, set up an Iceberg output target for customers' data lakes as well. So you don't have to use the MDL to use Splunk. You can use your own lakehouse, but we do support Iceberg for that. Good to realize that you don't have to put this made it out like the data has to be in Splunk. We can see the data even if it's in your own lakehouse as long as it's Iceberg tables in the catalog.
Right. For the promote feature, we also support that for like S3. So if customers don't want to use MDL and they want to route.
Yeah, many customers just build their own these days. You guys are probably those types of customers here. And so, the idea is to have visibility no matter where the data lives. And with Iceberg as a standard, and Parquet as an encoding standard, it's opened the door for Splunk to take advantage of it. We can, of course, our normal indexing is always there, but as I mentioned, it's less, it's more expensive.
Great. Any questions?
Okay, thanks very much.
Great. Thank you so much. Thank you.
Introduce yourself.
Yep, I'll introduce myself. Yep. All right, I am not loud. Let me know if you guys can hear me okay. Fantastic. Just making sure this thing works. A few announcements before I get started. So if you need the restroom, it is out into the left. Don't go outside, besides the doors right behind you, don't go outside the doors beyond that without an AWS rep with you. You will get locked out. So stay in the area with the food. If you need the Wi-Fi password, it's on the boards to your sides. So both sides of the room. Be sure to help yourself to food and drinks. We're not taking leftovers. So at the end, make sure that you're going out there and helping us out with that. That'd be awesome. We do have an overflow room. It doesn't look like we need it, but just in case, there's an overflow room to the side. Did I miss anything? Those are all the announcements. Awesome. All right. I'm going to go put this guy down so I stop messing with it. All right. So let's get this guy going. Fantastic. All right. So my name is Letitia. I am the Global Security Architect at ClickHouse. I've had various different roles over my 4 years with the company. Was there shortly before we actually launched the product, so I've been around for a little bit. What I'm presenting on today is actually more of a general topic for the group, considering that we're at an Iceberg Meetup. It's during RSA, and RSA theme this year is community. So wanting to make sure that we're actually addressing the community theme as well. Feel free to stop and ask questions if you like. When I was actually coming up with the presentation, it was funny because I was looking for like an image for a lake house. You ever look for images of lake houses? They're all like falling down, like old sheds and shacks. And I'm like, we're modern, come on. So I had to go and find like a modern house on an actual lake in order to represent that well. Otherwise, it looks like we're ancient. Like, no, we're not ancient. But just getting started. So I actually did a little bit more research for this specific meetup. A lot of the work that I do is really just educating customers on how to set up security within the database product and the database space. And really, the attack surfaces haven't changed, but we have AI coming into the picture. Everybody kind of is thinking about how do we deal with AI in modern architecture? How do we deal with this with lake houses, with analytical databases? And the attack surface is the same, but really what the target is a little bit different, because really when you're looking at threat actors, like threat actors are going to be going after your data. When you're looking at AI, the threat is a little bit different because there's different ways that threat actors can get at your data, and there's different ways that your AI could potentially interact with your data in a way that is not expected. So these are just some of the things that you want to go through and think about. Some of the threats to look at is really when you're looking at Lakehouse formats and you're looking at Iceberg, it's really that metadata poisoning. So when you're looking at metadata poisoning, what this is talking about is the machine-to-machine relationship expects that metadata is a machine source. It doesn't think that it's human. So there's a trust that's built between these machines. This is how the systems are able to operate. When that trust exists, it can be actually pretty easily broken. So you can get into things like hiding malicious data by just hiding it from when you're actually building AI models, hide it from the validation, but include it in the training. You can do this through metadata poisoning. You don't even have to get at the data itself. You just change what you're actually looking at. Same thing with schema partitioning poisoning. This is just really, masking the data or misleading the AI. So the AI might think, I'm going to use, this snapshot, and the snapshot maybe is an older snapshot. Maybe it has data in it that should have been deleted, and the newer snapshot doesn't have that data. These are things that could potentially cause data leaks. Vector poisoning, you can actually get irrelevant data that's coming from your LLM. So when your users are coming in and using your AI, they might actually be getting data that isn't relevant to their actual inquiry. So they might be getting wrong answers without knowing their answers are wrong, simply because the metadata has actually been modified. Next thing that could happen is snapshot manipulation. So snapshot manipulation can do a few different things. The most interesting one that I noticed was actually that snapshot bloat. Just crash your system. It's not even malicious, but it creates all of these little changes and all of these little writes. They'll actually cause your system to crash. So kind of keeping an eye on what is that AI actually capable of doing within my system. And then, I'm not going to cover everything here, but like privilege bypass. You have users. Users have a particular context that they're able to use. If your AI has more permissions than your user now has more permissions than they should. Just things to think about. These are not things that are hard to control for, but they're just new things to consider as you're adding that layer of complexity. This really just kind of brings us into needing governance around the models. And governance isn't a new concept. These are not new things, but there's new ways that we can implement them that make it less friction prone, make it less overhead for us to manage. So when I'm thinking about things, in my role, I really think about how do we put in the right guardrails so that we're not having to constantly watch and manage and add humans. So some of these things are like, the hardest one, finding owners. Anybody try to find owners? That's not easy. But finding the owners so that you know who owns the risk in each one of the areas. In the first diagram you saw, there was ClickHouse, there was Iceberg, you've got the AI models. Just making sure you know who owns what so that they actually understand what their part is in making sure that we have good guardrails. Second part, policy is code. Now that everything is code-based, you've got really good ways of being able to get into the environment and be able to manage things without having to do human reviews. Who wants to do human reviews? Those are old. It takes too much time. So making sure that you have scripts in place, making sure that you've got good infrastructure as code when you're actually applying things like permission policies, doing maintenance of your snapshots, making sure that those old snapshots that you expect to be gone are actually gone so that you don't end up with your AI going after the wrong data. Making sure that you've got property enforcements on your tables. So just a few things. And there's examples of these that you can actually find online. People have been creating content around the policy as code so that you don't have to start from scratch. And then the last part is just the cross-engine standards. So you've got systems that are connected to each other. So if you're connecting ClickHouse and you're connecting Iceberg, you've got two different table formats and you've got different schemas and different ways of being able to manage both of them. So kind of think about ways that you can keep those in sync. If you've got retention, making sure that you keep your retention consistent across your systems. If you have credentials, it's really making sure you're using that common set of credentials and keeping those permissions consistent across your systems. And then just maintenance, cleanup, again, not new concepts. These are all things that have been in the industry for a long time. It's just thinking about them a little bit differently, thinking about them more in programmatic terms so that as you're introducing AI to the equation, you have good guardrails. And last one, how you can help. So these are open formats. These are open source. There's communities that are built around all of these different technologies. So it's really about just coming together as a group and making sure that everybody's going to see different things in their implementations. Everybody's going to see different risks. You're going to see different things materialize because the way your users are using your system is different. Sharing that information is going to be really critical to making sure that we all learn from each other. We actually see what's out there rather than just hypothesizing. Making sure that we're contributing to tooling. So if you build something that works really well for going back to policy as code, you can actually share it externally and everybody can benefit from that. We're not all starting from scratch. It's really helpful to be able to share. But yeah, just going through and making sure that we're staying connected with each other. So questions? Everybody's still eating. There's dessert out there. I'm going to be the advocate for dessert. All right, so I'm just going to switch into just a little bit of introduction. So ClickHouse, what is ClickHouse? We are an open source columnar database, very, very fast for massive amounts of analytics. Also high compression rates, so it kind of keeps your costs down. Yep, we speak SQL fluently. We process data extremely fast. So if you're looking for something that's back in your AI, this is a good one. Or you're looking for something for your AI to actually query against, this is also good. Very efficient storage. And then scalable. You can really scale this up, scale it down, depends on what you need it for. If you would like to connect with us, there's a couple of QR codes that you can actually go ahead and scan. We've got additional meetups in the San Francisco area. So if you want to sign up for some of those, we bring lots of different participants together from the open source community to do presentations on things like, how they've used the technology, how they're contributing to the open source community. Of course, we've got Slack, so if you have questions, we support all of our open source users. And then PuppyGraph. Very grateful for PuppyGraph co-hosting this event with us. Couldn't actually do it without them. I flew out specifically to come and meet with the team. So PuppyGraph is basically that visualization layer on top. So you can query your tables as a graph, actually visualize them very, very quickly.
Sorry, just wanted to make it. Sorry, hi, my name is Zenny. I'm the co-founder of PuppyGraph. We are a graph query engine that can sit on top of your existing lake. We're doing more than just a graph visualization, and you're allowed to query your existing tables in Cypher or Gremlin. We're also agentic ready as well. So later on, our co-founder Waymo is going to have a talk, and he will dive in a little bit more. And feel free to flip it to the next one. Thank you. And then also we have a forever free Docker download. So if you are interested in trying it out with your Iceberg, feel free to just download the free version. We're also available on AWS and GCP Marketplace. We also have a Slack community. And then the last slide is we're available on LinkedIn, Twitter. Please, follow us. And then we also have tons of demo videos on YouTube. And then the next one, I think, is AWS.
Yeah. Hi, my name is Amy Krishnamohan from AWS, doing product marketing. Thank you for coming here. By the way, there's a drinks in the bag. I know a lot of people ask where is the water, so I want to make that announcement. And yeah, AWS is investing a lot in the Iceberg, from data ingestion to data storage and analytics, all the way down to AI. So I'm sure many of you are using the AWS services. So if you are really keen on Iceberg feature, please feel free to look at different services. And if you go to the next slide, there is a website where you can see a lot of information about how we integrate with the different types of Iceberg format in multiple services. So yeah, please, and then we'll have another session from AWS team to talk about how you can ingest the data to the Iceberg. Yeah.
Fantastic. And yes, thank you to our AWS sponsors, and especially for the food and beverages. Again, there's beverages in the back of the room. Water's all the way over there. And then coming up, we have several speakers that we're going to be presenting. So we've got Scaling AI Agents for Proactive Vulnerability Response by Yiheng. which is Cogent Security. We've got secure streams and open tables ingesting data into Apache Iceberg at scale on AWS by Austin. The Unkillable malware remains active by Yiheng, Chao, and Palo Alto Networks. See, and then building customer-facing agent systems in production on Apache Iceberg by Waymo. So really excited for the next speakers to come on up. And are you guys using?
Awesome. Thank you. Hey everyone, my name is Peyman, and today we're talking about how we're building a real-time security lakehouse within Cogent Security to power some of the enterprise scale context for our AI agents within vulnerability management. So starting off with a quick intro about myself. I joined Cogent over a year ago. Spent almost a year and 4 months since day one. And so right now I'm hoping to lead some of our efforts on foundations. So across the foundations, what we are doing is integrating a lot of customer data at enterprise scale into Cogent platform, which requires a lot of like big data ETL, which we'll talk about like different aspects of that. But my background has been primarily on platforms, different types of platforms in the past. Prior to Cogent, sometime in blockchain, working with Alchemy to build a data platform to index the blockchain data, logistics platform, how to do the vehicle route optimizations for autonomous vehicles, and earlier in Microsoft on AI platforms. So I'm going to start off by sharing an insight about the vulnerability management space and the general, and the general market trends that we have been observing that has led to us actually investing in this space and then like building the platform in a way that we are doing this. So in 2018, the mean time to exploit for like an identified exploitability was 2.3 years. And we're seeing that over the past like decade, this time to exploit is quickly collapsing. And in 2026, that has got down to 1.6 days. It's a huge drop. And with this current rate, it is expected that soon enough we'll be within minutes of being able to exploit a vulnerability. And so from the exploitability perspective, like while we are having this collapse of time to exploit, on the other side of the story, it's very interesting to observe that more than 50% of the vulnerabilities that are identified remain to be unresolved after 2 months of being identified. So the attack rate is pretty high. The defense rate is not as high. And this, coupled with the next observation that we have about the market, is at the very same time that the time to exploit is quickly collapsing. The number of vulnerabilities that have been identified in the past decade are just going up. And even in the most recent years, the slope is accelerating. So over the last decade, we've seen more than 7x growth in just the pure number of CVEs that have been reported, which is very valuable in input to the vulnerabilities. And this effectively means, combined with the like time to exploit insight, the attackers are well set to be able to exploit environments within minutes, while the defenders are actually taking days to weeks to respond to the exploitabilities. And Cogent, we believe that this gap is actually an execution gap. And this is happening not because the vulnerabilities are hard to be identified, but fixing those vulnerabilities remains to be the hard problem to be solved. And that's that's where we come in. I mean, and that's what we're trying to help with by building a platform that helps defenders to prioritize, contextualize, and remediate the insights that are collected. So to get a better understanding of why there is such a big gap, it's helpful to understand where the legacy vulnerability management solutions are falling behind. So a typical workflow of vulnerability management starts with picking up some signals from scanners like policies of the world, Tenable, CrowdStrikes, and then typically these signals are provided at scanning time of the environment. But at this time, the vulnerability management workflow is not actually ending. It's quite the opposite, just beginning. So after these insights are collected, the very first step is to contextualize all of these insights, to be able to correlate the signals that have been identified by sources, which is often a heterogeneous, noisy signal kind of problem. We have a lot of noisy signals, and then we need to clean them up and correlate them. And so this process has been somewhat of a manual process in the legacy vulnerability management. After the context has been added, then we need to take actions on okay, based on the insights that have been figured out, what are the priorities, what actions need to be taken. And typically in the traditional workflows, this is where some tickets are being dispatched, some spreadsheets are being generated, and finally operationalizing the fixes through remediation process that often involves an interaction between engineering, IT, and security departments, which is a huge kind of overhead, and leading to days to weeks of the end-to-end process of the resolution. So where Cogent comes in to add value is by helping to make the contextualization, prioritization, and remediation process more automated and more up to speed with the rate of exploits that we're seeing in the market. But before we even get into defining a solution here and understanding what solutions help, it's also important to understand the scale of the problem that we are trying to solve. So part of the process part of the reason that the process of contextualizing and prioritization is very challenging is due to the sheer volume of the data that is typically in the space. So in Cogent, with some of our largest customers, we are seeing more than 10 billion data points and more than 100 million changelog events per day, which immediately puts this problem into a big data problem. And if we were just to tackle representation and storage of this data, this will be over hundreds of tables that needs to be that needs to be in place to hold this data. So this scale problem is actually an extremely important part of what we need to understand before we tap into any solution. And because this helps us to identify the properties of the solution that needs to be true, regardless of what solution we take for this problem. So at this scale of big data, so in order to have effective prioritization, effective contextualization, and remediation, there's a lot of slice and dicing of the data that is needed. There's a lot of assessment and analysis that is needed. So query performance at scale is one of the most important properties of any solution that needs to be in place. So another important property of the solution is schema variance and drift. So across different integrations, it is extremely common for the data that comes from multiple sources to have large degree of variance on schemas, the sources change, and we shouldn't be taking any dependency on a specific set of schemas, and then we need to handle schema evolution as a first-class native citizen of the solution that needs to be adopted. The third angle is audit and reproducibility, which is often needed by some compliance within the space that requires us to be able to reconstruct the state of customers' environments at from an earlier time, like being able to do time travel and then like redo the ingestions and answer some insights from some earlier point in time, like being able to audit the data like through the lens of time as well. And finally, due to the different multitude of use cases and different requirements of the solution, so we need to have a solution that allows us to choose the right tool for doing the data processing. And in big data landscape, there's so many different ways to handle the data. I mean, there's so many different batch techniques as well as like streaming techniques, and a lot like later on we're gonna see some presentations on about like how we can use context graphs and like you use Puppy Graph as the graph engine. So there's variety of tooling here. So it's very important for us like to be able to choose the right tool to solve the right problem, and the solution needs to have like some level of friendliness towards these properties. These requirements are the reason that we landed in using Apache Iceberg as the kind of consolidated and consistent foundation for like processing the data on the storage level. And right off the bat, I mean, like we get a lot of like properties of using Apache Iceberg. For instance, we got like the time travel is something that comes by default. We are able to go back in earlier snapshots, be able to audit the data, be able to reconstruct and reconcile the data. Schema evolution support is pretty strong in Iceberg. So the partitioning helps with like easier performance, I mean, like more performant queries, and like a lot of ecosystem support for different engines, like whether it's Spark, Flink, Trino, like now Puppy Graph. So there is a very rich ecosystem of like the engines that can be used to like slice and dice the data. On top of that, you're not losing on ACID transactions as well as like compaction and maintenance properties of Iceberg. And that's why we thought that, okay, Iceberg sits at the center of like the solution that we are leveraging here. Okay, so going back to the problems that we identified earlier, there were three main problems that we touched on. The two kind of like domain problems that like we started with were part of like one on scaling, like it's a pretty large scale data problem, as well as a lot of manual touch points in the legacy workflows. So in order to handle these two problems first, so we need to have some level of transformation that is handling high throughput data analysis as well as transformations at ease, and allows us to bring in automations and orchestrations into the mix that helps us to reduce manual touch points throughout the process. That's why we kind of started with using Spark as the transformation engine coupled with processing the data on Iceberg. So the typical like modernized workflow of like the ETL like through this platform-wise approach is like the sources can still be extracted from data can still be extracted from the sources like Colin, Tenable, Liz, and CrowdStrike. And like the data is going to be ingested into the Iceberg layer as raw data. Now we have different layers of like cataloging the data and like kind of promoting the data through the data transformation ladder through time. And this is where we are using a lot of like transformation like functionalities, like being able to deduplicate the data, enrich the data, score the data, contextualize the data like across different sources, and get to the state of fully transformed data. But obviously, we don't want to use Iceberg to power all of our product use cases. So the product use cases, depending on a use case, may be a better fit for an old TP kind of serving layer, and old layer like Postgres, or an old app layer like Lakehouse. So we use Lakehouse for a lot of our analytical queries, as well as like Postgres to power a lot of like product use cases. So with this kind of like setup, we have solved for one main problem, which is scale. But in order to reduce the manual touch points that are like present across the industry, we need to have like an orchestration. And that's why we are actually wrapping all of these operations in a very like orchestration-friendly framework through Temporal. So we can like at ease like modify the different workflows and like bring in the automations as needed. So combination of temporal orchestration as well as batch high throughput ETLs with Iceberg and Spark allows us to tackle two of the three problems that we touched on early on, which is the manual touch points and scale problem. But still, we will not be able to handle the exploits under minutes. Because the next attacker is not going to wait for the next scheduled one of all of this ingestion to land and then do all of the transformations. These ingestions, by definition, are time consuming. Multiple hours. It's still not within the kind of by minute level kind of actionability that we want. And in addition to that, some signals that needs to be consumed in real time from users, like changing ownership, changing assignments, and then all of those things need to be immediately reflected on the data that we are serving the customers. So in order to tackle that, we needed to add a real-time streaming layer on top of the existing architecture, which is where we are introducing a stream processing engine like Apache Flink, where we are able to do stateful streaming processing on top of the Iceberg data and do true event processing in a real-time fashion. And so the sources of the events can be anything from the real-time sources, there may be a 0-day, there may be some source that is providing webhook data that needs to be integrated, and then we need to immediately act on that. Or it can be a user initiated action, some change of ownership. And the user initiated actions are often happening on top of the product that is powered by the OLTP layer. That's why we often use the CDC pattern and Kafka to handle the data in motion, and then do real-time transformations on top of this data, and be able to handle the real-time workflows. But one important observation, one important requirement here is that we should absolutely avoid for kind of separation of sources of truth between the real-time and batch sources. That's where, again, Iceberg is extremely helpful here, because Iceberg not only has a strong support for batch use cases, but is having pretty real-time friendly kind of capabilities, very nice integration with Apache Flink, and so we can still get to use the same source of truth across both our batch and real-time use cases. So with this, we will be handled to finally, handle the by minute exploit risks that are going to be the near future, and handle both of these scenarios. But we're one step away from just being done with our end-to-end solution. So where do the agents come from? So we mentioned that the process of the traditional vulnerability management workflow has three main components, contextualizing, prioritization, as well as remediation. So contextualizing and prioritization, actually, contextualizing is having that really easy integration within classic ETLs. But when it comes to prioritization and remediation, sometimes the advanced reasoning is something that actually is needed to move the needle. And that's where a lot of human inputs are right now being used to move the needle. So if we truly want to be on par with the by minute kind of exploit times, we need to have advanced agentic reasoning on top of the same source of truth that we're having. And that's why we're having our agentic layer also powered on top of Iceberg. So now this lands us to the one consistent foundation that powers several use cases. The high throughput and kind of higher latency workflows that are deeper in nature through batch processing on top of Iceberg. The real-time processing that are kind of lower in scale usually, but needs pretty fast latency through Apache Flink on Iceberg, and advanced agentic reasoning that helps us to have customized workflows by agentic layer on top of Iceberg, all leveraging the same source of truth and consolidated foundation for powering a lot of our data use case, for a lot of our product use cases like AI prioritizations, dashboards, reportings, as well as providing context to a lot of downstream workflows. Okay, so what we covered in this presentation is first understanding that okay, a lot of the problems that we're trying to solve in the vulnerability management are naturally big data problems. So there is a very big data presence in the problem that we are trying to solve. So that's why it's very helpful to have leverage from the modern architectures that support big data. Apache Iceberg as a foundation has like the nice properties that are needed for time traveling, like queryability as well as schema friendliness, and like ease of integration into different like transformations, and using Spark for batching as well as Splunk for real time, and agents to be powered on top of the same canonical source of truth, and one consistent foundation for every product data. So with that, if any of these topics are of interest to you, we have recently raised our Series A, and we'd love for you to come and join us and help us to build this. So we've had our Series A from BCV and Greylock, have offices in SF and New York, and please check out our website and yeah, look at the Curious website.
Any questions? Oh, there you go.
Sure.
So how do you identify what to be processed as a batch and what data source need to be processed real time?
Great question. So this is typically a use case by use case kind of scenario. For instance, like if the scenario requires immediate actionability, like a user has provided some input, and the user expects to see this correction to be immediately applied. That's a real-time use case. If you're handling a 0-day, for instance, like we cannot afford to spend about like 6 hours of ingestion, so we need to immediately take action on that, alert the customers on that. If there is an internet protocol, if there is a port that is exposed, and like there are some use cases that are more time sensitive, and then there is a very high cost of kind of late action, and those are for streaming use cases. But typically, the batch is the higher throughput and like deeper transformation power on top of that.
Any other questions?
Awesome.
All right. Thank
Thank
you.
you.
Test. Yeah, good. Yeah. Talking to you right now. Let the room settle a little bit. Yeah, cool. Thanks, folks. So I'm your next session of the day. You're stuck with me for the next like 20 so minutes. There will be a 10-minute break after this, so don't worry. Let you loose here pretty soon. But my name is Austin Groeneveld. So I'm a data streaming specialist solutions architect with AWS. So what that means for me is that I cover our Kinesis data streams, Amazon Data Firehose, managed Kafka, and managed Flink services on a day-to-day basis. So anything that pulls in one of those 4 services will bring me in. So I by no means only work with those 4, especially in the context of data streaming. I think as a question from the last session kind of asked very nicely, like when do we use data streaming? When should we do something in real time? So of course, the first obvious benefit of doing something with data streaming is you're getting real-time analytics, real-time insights, generating those insights from sub-second, minutes latency, if we're talking more near real-time. But the second main benefit of working with the data streaming architecture is that it actually unites data silos very, very nicely. So in any given data streaming architecture, you're going to be uniting data coming from multiple different sources and then fanning that data back out to multiple different interested destinations. So while I don't cover S3 tables, Iceberg itself, I think I was invited to talk a little bit about how to stream data into Iceberg tables and how I'm seeing customers do that on a day-to-day basis. So if that sounds good, first I'm going to start with an Iceberg use case. I've spoiled the slide already. It's going to be a CEC use case. As much as I do like talking about data streaming, just for the love of the game, I think tying it to a use case will make certain concepts, and when we look at specific services, make it a bit easier to digest. And then I'll have two main kind of content portions when it comes to the building, like how do we see customers build these stream pipelines to Iceberg tables. And first option, or will be number 2 here, will be no-code, low-code streaming ingestion tools. We'll talk about Amazon Data Firehose. And then third, we'll spend some time talking about Apache Flink ingestion with AWS. And specifically, when I cover Apache Flink, that's the managed service for Apache Flink. And then finally, at the end, some streaming caveats, things that I see customers doing across Firehose, which is going to be our service that I recommend customers to use when they want the least amount of engineering overhead involved with syncing data from a data stream into Iceberg tables. And then we get all the way to Flink, where I see the most engineering overhead and where the managed service for Apache Flink can let customers get involved, write Flink code when they need to, but stay away from managing servers as much as they would want. So with that said, quick core concept and just discussion of streaming CDC change data capture. So it came up in a couple of previous talks, so I really don't want to spend too much time redefining the term. If folks here are familiar with it, do stop me if you're not. But the use case I'm going to follow today is we're going to take data that is coming from a transactional database, or OLTP layer, serving some kind of transactional operational use case workload. And we're going to talk about how we can do CDC from those transactional databases using a CDC tool. Most popular tool that I'm seeing with customers right now is Debezium in the Kafka Connect ecosystem that lets them both read data from their transactional data lakes, or transactional databases, sorry, as well as more audit layer information, like who did this alter row, who did this update, who did this delete, and you can stream all of that data from your source databases into Iceberg tables downstream. And so we'll talk about these services in the middle. Amazon MSK is our managed service for Apache Kafka. And then our 4 ingestion layer services will be the next 2 sections of this presentation. But for me, for the start of this year, I'd say the past year, when I talk to customers that are streaming data into Iceberg tables, CDC use case has been by far the most popular across the board there. So again, in this ingestion layer, I've started with Firehose at the top being least amount of engineering overhead needed. We're not going to talk too much about the Iceberg Kafka sync connector. We will be spending time with Apache Flink, and I do have Amazon EMR here that is representing using Spark structured streaming. I'm not going to spend too much time on that today. There are a lot of cool advancements happening in the Spark structured streaming space. I need to catch up on them myself, and then maybe I'll catch y'all in the next talk to talk about them in a bit more detail. But for today, we're talking about Firehose, Apache Flink. That sounds good. We'll keep moving. So very quickly, Firehose offers a no-code, low-code, easy-to-use solution for delivering real-time streaming data to Apache Iceberg tables. All you really need to configure with Firehose is say, hey, what am I reading from? That could be a Kafka topic, which is the Kafka abstraction of a data stream. That could be a Kinesis data stream. That could be anything you're putting onto a Firehose data stream using the put records API that Firehose does expose. So benefit of using Firehose, you are using first-class AWS primitives. You are delivering data to Firehose using APIs and all of the nice privileged access, least privileged access controls that come with using IAM. And all the native integrations across AWS, be it with S3, Iceberg tables on S3, AWS Lake Formation, and so on. All you're configuring buffer hints. So we'll get into this in a bit more detail as we get to the streaming caveats, but anytime you're talking about streaming data into Iceberg tables, it's going to be a balance of how quickly can we do this versus how many small files can we bear to deal with. Because if you push too many small files into your Iceberg data lakehouse, it will start to show some cracks under the pressure. So trying to find that nice balance of how long can we afford to buffer data to get some nicely sized files versus how long can we actually afford to wait to derive our insights is kind of the key balancing act for this ingestion layer. Be it Firehose, be it Flink, we'll see this across both. But when it comes to Firehose, this is effectively all you're doing. You're giving it some information about Iceberg table routing, saying, am I writing to a single table? Am I writing to multiple tables? And you can do that using some inline or even custom Lambda transformations. If you want to have some more custom logic, you can always use AWS Lambda on top of a Firehose data stream to do so. But that is effectively all I have for Firehose. Super nice and short and sweet. Any questions on Firehose before I move on and spend a bit more time talking about Flink and why I think it's really cool? Perfect. So I do want to land back here really quickly and just say, when it comes to using Apache Flink for writing to S3 tables and Iceberg tables on S3, there are some things to keep in mind. And before, this is the slide I was looking for, before I get into that in too much detail, I also want to point out, it won't be a huge talking point for the talk today, but we're also seeing in the context of the medallion architectures, which has come up in the last couple of talks I've heard as well, when it comes to, we're going to write data to a raw layer in our Iceberg tables or a raw layer on Amazon S3 before moving that data into a bronze layer, a silver layer, something that's ready to serve consumption applications. A lot of the time that's done with batch workloads. Apache Spark does that very, very well. But as I see customers maturing, seeing fewer and fewer code changes to those layer-to-layer batch jobs that are running and pushing those updates. We see more and more customers moving into the streaming frameworks, be it Spark Structure Streaming, be it Apache Flink, to read data from S3 and Iceberg tables and write it out to their next layer. So that's not going to be a huge talking point for the presentation here today, but it is a growing trend. So let's now talk about Flink in the context of our upstream CDC use case, right? We're taking data from our upstream operational transactional database and the audit logs provided to that, and streaming that downstream to our Iceberg tables with Apache Flink. So before I talk about the managed service for Apache Flink, let's just talk about why we're talking about Apache Flink in the first place. The Flink Iceberg connector comes with a suite of very, very nice features. For folks in the room that may be not super familiar with Apache Flink, it comes with a handful of APIs, so you can choose exactly how you engage with Apache Flink and the underlying stateful stream processing capabilities that it provides to you. So for the Flink Iceberg Sync connector, you can use either the data stream API, which is the Java, Python, Scala, full control, essentially, version of programmatic implementation with Apache Flink, or you can use the Flink SQL API, which is more, let's translate and do everything we want to do with SQL actions and keep it that way. Flink Iceberg connector does very nicely with both. Internal Flink construct known as checkpoints. This is how Flink keeps track of its state, implements things like fault tolerance and resilience for its data, as well as establishing exactly once semantics for delivery here. The Flink Iceberg Sync connector leverages these checkpoints and integrates them with Iceberg snapshots to keep track of points in time and when writes to Iceberg tables are ready to go. And so it plays into your downstream Iceberg time travel capabilities very nicely. The Flink Iceberg Sync connector is supportive of append, overwrite, and upsert write operations, whether you're going to be inserting, whether you're going to be updating a table and overwriting data in that table overall, or providing upsert, where you're going to have Apache Flink address a delete file and an insert file and increase the amount of small files going into that downstream table. Flink supports all of these. It also supports branch writes. So if you don't want to write to the immediate main branch of your Iceberg tables downstream, and you want to instead write to a staging branch, a developer branch downstream for testing capabilities, you can use that in Apache Flink. And the two things that I want to spend more time on in the latter sections of this presentation will be embedded maintenance operations, because like I said, when it comes to streaming data to Iceberg tables, it's all about that balance of how long can we batch this data, buffer this data so we can get some reasonably sized files versus we need this quickly. So the new Flink connector versions for Iceberg Sync connector has some cool new embedded maintenance operations embedded, and as well schema evolution. We're going to talk a bit about the dynamic committer and the new Flink Iceberg dynamic sync here in a moment. But quickly, why managed service for Apache Flink, and what does it do for you? So one primary benefit of Apache Flink, and reason I'm going to provide it to you in the context of, we started with Amazon Data Firehose, and we talked about low-code, no-code solutions. Flink is going to be the absolute converse version of this solution. In the middle, you're going to have the Kafka Iceberg Sync connector, still low-code, still creating your own configuration or bringing a connector out of the box and implementing configuration according to your specific specifications and needs. But Flink represents, we need full programmatic control, but we don't want to manage any of the underlying infrastructure. So Amazon Managed Service for Apache Flink lets you bring your own jar file. You can do your local Flink application testing locally, deploy a local Flink cluster, test it, package it up, and then submit it to the Managed Service for Apache Flink, and it will run it for you. You get per application level resource isolation. So while it is a fully managed service and all of the backend infrastructure management is abstracted for you, you're not worried about whether it's your other managed service for Apache Flink applications or other customers' managed service for Apache Flink applications. None of them are contending for resources. Each managed Flink application gets its own dedicated Flink cluster by default. They're also highly available by default, both on some internal Flink constructs like the Job Manager high availability, as well as more AWS-specific constructs such as availability zone failover, AZ failover, that is resilience of an application within a region on AWS. And then finally, things like automatic state, the checkpoints that I mentioned before, save points, or Flink snapshots. All these things are automated and handled for you and enabled by default, all configurable for you, but implemented by default. And managed service for Apache Flink is secure by default. So encryption at rest, all application state, checkpoints, save points stored and managed for you by the managed service are all encrypted at rest. And in transit, whether it's data transferring between internal Flink nodes, internal nodes on the Flink cluster, or to the external sources and syncs, that encryption in rest is supported by TLS. And finally, because you're talking about AWS native services, you're getting all these native integrations with IAM. And so all permissions assigned to the IAM service role that you associate with a given managed service for Apache Flink application inherit all of its service level permissions internal to the Flink application in the context of Flink connectors. So the Flink application, as you deploy it, will only be able to read from or write to a given S3 table bucket, Iceberg table on S3 that you give it permission to, and all that is defined in one place using the IAM service role assigned to the managed Flink application. Now let's talk a bit about how the Flink Iceberg sync works. So let's say in our CDC use case, at a small scale, you were leveraging, say, or replicating from 10 tables upstream. And all that meant for you is you had 10 tables then represented as Kafka topics on your Apache Kafka cluster, Amazon MSK, perhaps. And say you were setting up with the Firehose solution, just 10 Firehose streams, one for each topic to replicate. Each one is replicating a one-to-one mapping of that topic to a downstream Iceberg table. Things were easy to manage. As you scale up, you might be managing somewhere from hundreds to thousands of Kafka topics representing upstream tables. And so, flipping slides again, Apache Flink still allows you to operate at this scale, but you essentially, before the application is created, need to determine a one-to-one source table to destination table mapping that Flink could manage for you in the form of a directed graph, but it was static. So at application launch time, the downstream Iceberg tables need to exist, and the upstream database tables in your transactional database are set on a specific schema, and whatever that schema is at the launch time of your Flink application only handle data of that schema. So if the upstream database schema were to change, the Flink application, as it continues to run, would only be writing data in the previously known schema. And if the schema were to change, it would not only be able to not reflect that new information, but also wouldn't be able to generate a new table downstream if that is of need to you. So enter the Flink Iceberg Dynamic Sync. When I mentioned before the static implementation, that was true of either implementations where hard-coded schema or using a schema registry. The Flink Iceberg Dynamic Sync will utilize a schema registry such that you can now dynamically, and without having to manually restart your application, which would mean downtime for your Flink application, potential business loss revenue as you restart your Flink application to update configuration changes for either table information or schema information. Now the Flink application can dynamically pull and interact with a schema registry to understand schema changes. And in this way, it can now support things like, of course, schema evolution, but as well as dynamic table routing, which was not possible before with a static sync connector, as well as downstream dynamic table generation. So now with upstream schema changes, you can configure your Flink application to create new tables for those schema changes if that is to your use case. And second call out, as it does this with the schema registry, the other important thing is that Flink is changing its abstraction of the record itself. So if I go back to the static one, you can see Flink is doing internally, taking from the Kafka source the incoming data in the form of raw bytes and converting it into a row data converter application here or operator here. And on the dynamic sync side, it's changed to a new construct known as the dynamic record, which is preserving all of the metadata of the upstream record, its schema, and therefore it can interact with the schema registry intelligently so it can know what was the previous schema, has it changed, what operations need to be taken from here to dynamically make our changes downstream in Iceberg. So a few streaming caveats. As I mentioned, it's a balancing act. So anytime you're introducing a streaming layer into your Iceberg tables, the one issue or the one problem you will first run into is, hey, I have a lot of small files all of a sudden. How do I balance this? So this comes from a couple of things. Of course, with data streaming, you're talking about continuously generated data coming in at hundreds to thousands to tens of thousands to hundreds of thousands of records per second. And you need to balance, and that comes with many, many commits to Iceberg. And with each commit to Iceberg, or with each write to Iceberg, there's a commit to Iceberg. So you're generating many, many small files. On the form of an insert operation, you're just adding an insert data file. But if you've also trying to, and this is very common in CDC use cases, which is what I'm trying to frame this presentation around, you would then want to update downstream tables in an upsert mode, which generates first a delete file, then an insert file for that particular record. So you're essentially doubling the amount of records per file. And if you map that out, to skip to the bottom here, no shuffle or sort before writing, if you're mapping that out to writes to multiple partitions downstream in multiple tables, you're increasing that factor of If you have n tables and m partitions, you're increasing that factor, the number of files by a factor of n times m. And finally, with writes, in a data streaming context, Apache Flink is doing this by default. Same with Firehose. They use merge on read Iceberg semantics. So that is, it's going to prioritize speed rather than read performance. So it is going to be writing in data. Instead of doing a full copy on write, which is essentially on this write, I'm going to delete the whole table, replace it with all new data, which would mean the write is very slow. But then on the read side, data can come in and query that table immediately as is. There's no work for the query engine to do. On the merge on read side of things, it's prioritizing writes to the table. It's only providing files in that delta of changed data. However, when the read query engine comes in, it now has to do a lot of sorting, a lot of deduplication, compaction, what their operations might be required to dedupe the amount of data files and come to the new source of truth at a certain point of time. So small files increase the workload on S3. S3 tables is going to be our Amazon native version and fully managed version of Iceberg tables, but of course as well for Iceberg tables on Amazon S3 buckets normally. And so when you talk about managing small files, I hinted at it before, but when they land in that destination Iceberg table, compaction becomes a first-class priority for the performance of your Iceberg tables. You cannot treat it as an afterthought. You need to be compacting your Iceberg tables regularly to ensure that these small files are being compacted to usable size files. And how frequently you're running those compaction jobs is also critical to ensure the uptime and availability of the actual Iceberg tables themselves downstream. So what you're seeing here is a naively scheduled data compaction job. So in green, you have our continuously running Flink applications. These are trying to write to these Iceberg tables continuously. And in the blue circle here, you're seeing our compaction jobs that are trying to run regularly to take these small files and condense them into smaller or fewer larger files. However, they're competing on that Iceberg table for the same lock. So if the case comes where a merge into statement is issued by the query engine after a certain amount of writes, the compaction job will fail until your next periodic run. And therefore, you're dealing with buildably small files. And after X number of failures, your small files have never been condensed after X amount of time. And your small file problem is increasing and increasing and increasing. S3 tables has some cool optimizations here. It does the compaction for you automatically. And it has some cool things going on behind the scenes that can help alleviate this pressure. But even still with S3 tables, small files can very quickly overburden the system. So one cool thing with the new Iceberg Flink sync connector is ongoing table maintenance in the running Flink job. So with the new 1.10 sync connector with Apache Flink, you get embedded table maintenance. That means while the Flink streaming job is running, you're getting table maintenance from your Iceberg Flink sync connector operator in the Flink application. It is taking care of expired snapshots. It is taking care of rewriting data files and compacting some small files for you. Not to the full extent of a compaction job on your Iceberg tables, but is doing some of the cleanup for you as it's maintaining its internal state over time. It's also deleting orphan files for you, as well as doing some new cool improvements on lock management. I'm not going into too much detail here today about that, but it provides more concurrency, a better concurrent access to the downstream Iceberg tables with some specific optimizations, as well as improvements in data consistency and resource management. And that is what I have. I'm hoping this will be open for questions, but thank you so much. If not, it's been a pleasure.
Question.
Please.
So what did you find there? So how did you find the managed actions? Not managed, but actions
For Iceberg, sorry.
With the new embedded maintenance,
Yeah.
the degree of improvement,
Yeah.
I would say when I talk to, the best way I could probably answer this question is when I'm talking to customers on their managed Flink applications and they're talking about, do we need to incur downtime for version upgrades or for, whether that's for the actual Flink version or for the internal like connector versions, a lot of times we're finding that it's worthwhile for them to do a restart just to upgrade the sync connector. Say, hey, you're going to incur some downtime on the Flink application because anytime you're changing a configuration, underlying parameters, the Flink application has to stop, save its state, restart. So there's some downtime in the context of streaming workloads that can incur a cost, right? You're running real-time analytics for a reason. But the performance improvements from this new sync connector version tend to, across the customers I've been speaking to, have been worth it across the board.
Any other questions?
Right on.
All right, thank you. Yes. We have a 15-minute break and feel free to use the restroom, get some beverages, and also some more food outside.
My name is Jeff. I just graduated from Cisco for the data science program. I'm actually working with a professor. We're curious about looking at jobs. So I was wondering if I could connect with you and we can ask some questions.
Yes, absolutely. And my colleague actually, she just recently graduated from USF, not UCSF.
UCSF.
Yes. But yes, we'd love to connect, and then I will also. Because oh, thank you, thank you. You know, I actually wanted to introduce you to our founder, Remo.
Oh, okay.
Because he has a PhD.
Oh,
so he knows
I'll
the
ask him all the
research.
questions and
Yes,
research
please, please, please.
All right. So scan. Thank you very much, Cindy.
Thank you.
All right. Cool. No, I'll bother him.
Yes, absolutely. And then let me find mine.
Yeah, it's really hard. No.
Hi.
Hi.
Hi. Nice to meet you. Hi.
We've been corresponding over emails. I just wanted to say hello.
Oh, that's great.
From the Atlanta meetup.
Oh, yeah. Oh my God, you made it to San Francisco?
Yeah, I did, yeah.
Oh,
Well, I
wow.
used to live out here, so I only temporarily lived.
I see.
Yeah.
Yeah, because for Atlanta, I mean, people warn us that
There's no one there.
no one there, yeah. Yeah, because we did a massive LinkedIn outreach campaign, and nobody even know what it is.
So I'm based in Atlanta, and I've been kind of experiencing.
Yeah, like nobody even know what, like I Salesforce or AWS, and so I have no idea what it is.
Yeah.
So I was like, well, okay. I mean, if you work for a fair company and still don't know this technology,
That would be unthinkable. So Atlanta is definitely it's more consumer focused.
It is. It sounds like because when we reach out, like some banks and a lot of like like I know like restaurants.
And banks, I don't think will be migrating to Iceberg. I would be shocked if they would never tell.
Exactly. Yes, correct.
Yeah, that's what I've been running into maybe like 2 weeks ago.
Oh my God, I'm so glad you made it. Yes.
For sure.
Yeah. Are you moving back? You're going back to Atlanta.
So I'm moving back, but not until probably summer.
Oh, okay.
So for now, I'm just kind of flying in at the start of the month and hanging out. So I'll be back for the Iceberg summer.
Oh, that's perfect. That's perfect. Yeah, and then you go back to the Bay Area, you will post a lot.
Yeah, so I'll make sure to stop by.
Yeah, please subscribe to our calendar. We'll definitely announce it there.
For sure. Yeah. Nice to meet you guys.
Thank you. So hi. And I want to introduce you to this.
Jargon.
So Jordan is a student at the UCSF, and he is actually one of the
Oh, yeah. So he actually did a lot of work on it.
Are you using Slack as well?
I don't actually use Slack outside of
You send it your email address.
Okay, for sure, sounds good. How long have you guys, how have you been staying with us? 3 years. Okay. What we
Right here. Can you plug in?
我们去 RSA
好了，啊，你好，你好，你好，对对对，来了吗？来了吗？可以了，可以了，可以了，可以了，来。我们就两做三个。我们三个。我先看，我这边发叫人，发叫 AWS 的人。哎呦呦呦！ Yes. Yes. You will publish on the. Anything is fine, but I first where I can do that. I'm more interested in the particular talk. Yes. Would love to listen in again. Yay! So what's your name?
My name is Rohan. I work at IBM. Sorry,
Oh,
I have
IBM.
an injury.
Oh, no
Let's do
worry.
this way.
Yeah. So let me show you. So
You will be recorded. It will be published on YouTube.
It's on YouTube, correct? So YouTube, there's something called Apache Iceberg Meetup.
Okay, this is where you will have.
There's Apache Iceberg Meetup. So
and they have and then the playlist. Oh, this is.
We will live stream. Do you?
Oh, this is so nice. And then you will keep this live stream on. I mean,
correct.
If I click on the live section, this
You
will
will
be
see it, yeah. And then we will, the AV team of AWS, they will process them into individual videos,
and then that will be also published.
That will
on the
also
same.
be published.
Thank you so much.
Yeah, of course, yeah. Some the live stream 啊，你们放上东西 live stream 都上就上了。Yeah, there's a Palo network. Oh, speaker. They're testing too. Yeah. 哎，来了！哎，可以了！啊，可以了！可以 ，OK。哦，Yeah. And also.
Me too.
Yeah, that,
Okay.
yeah, that's the green.
Yeah.
All right. Okay. Hello, everyone. We are security researchers from Palo Networks, and today we're going to present like the recent interesting finding we found. The unkillable malware remains active. So I don't know if you guys are familiar with this CVE, but let me give you a little hint. This CVE actually have a name called React to Shell. So this was being reported to the community on November 29, and I remember there's a Friday. Yeah, there's a Friday where the POC has been published in the GitHub. Well, if you're a security researcher, you know what that means. It means you need to fix it, add coverage during the weekend. So that's fresh mind. At the very next week, Monday, Palo Alto Networks released some coverage, and at the next day, Tuesday, we started to detect there's a lot of exploits against the CVE, and also there's not the exploits. It's not just from the fun kit. It's not from testing. It's actually intent to implement or deliver some malware. So I don't know if you guys are familiar with this. I'll give you a quick introduction about how this happened. So React has a very good concept called React Server Components. It's basically to load something in server side, not in the browser. So don't have to open the Chrome tab and this time consume you 1 GB of memory, something like this. So it's good. But there's also some security risks because, for example, for this one, React to Shell is failed to restrict the prototype access. This omission allows attacker to use the crafted reference path to traverse the JavaScript prototype chain and manipulate sensitive attributes like the proto. And also, a constructor would actually exploit this to forge a malicious object that replace the internal methods such as the form data.get with the native function constructor while having a malicious payload inside the prefix string right here. And ultimately, when the React server's async state machine attempts to resolve the manipulated object as at a promise, it compiles it and executes the hidden payload, resulting in the remote code execution in the server. So this is the actual payload. This is the real payload we capture in the wild. So the attacker is trying to use this kind of methods chain to deliver the malware. The malware, actually, we mark the malware host in case of anyone to trying to download it. And it's a downloader, and in the downloader, it will download the actual malware. We use Poppygraph to help us to draw this picture. And also, since we captured from the traffic log, from the thread log, the log is like a trillion gigabytes. It's a gigabytes. It's a lot of data. So we use Iceberg to handle this kind of big data. It gives us efficiency to process it, to add, delete, or adjustment. And we use Poppygraph engine to build up a series of functions. The function includes some botnet identification, tracing functionality, and we have successfully identified the botnets. In this two picture, you can see there's a isolated island. At the center of the island, this is a C2 server we have identified. And surrounding this C2 server, all of them, the nodes are victims. And these are the active C2 server. So again, thanks for the Iceberg and Poppygraph. We are able to build up a tracing dashboard. So this dashboard is every entries means a C2 server. There's just our real world C2 server and still active. We choose the C2 server, and also we can trace the victim numbers. You see, it's very high. And because we have the powerful tools, we can trace it and process it every day. In the time series, it gives us a trend. You see, we identified a lot of botnets, and we can see in which state botnets is very active, in which state botnets is going silent. Yes, the very interesting thing is that like we analyze the botnet, we analyze how this botnet deliver malware and what kind of malware it delivers. So we identify very interesting things. It's like we identify malware emoji, which is like very, very famous and very powerful malware. It's leveraging P2P protocol, but the author has been arrested and we think the malware should be gone, but actually it is not. So my Chao will take the remaining part to introduce that.
Hi. Yeah. So if you, I'm not sure if you guys are familiar with this botnet, Mozi. So it's like the one of the most famous or infamous botnet in the history. So I would like to call it a headless hydra because there's no central command. For the traditional command and control botnet, there's always be there's a headquarters. There's also there's always a C2 server. So for our security company or security researchers, if we want to take down a botnet, we always find their C2 server, we shut down it, or we just take control over it. And but for this one, for Mozi, it's different because it uses a customized DHT, distributed hash table protocol. So it turns every infected router or the camera into a communication hub. And another thing about the Mozi is it's a gossip style configs and it's golden key. For example, if the operator of the botnet, they want to issue some attack or they want to issue some new command to the whole botnet system, they use they use an object called config, in which will spread like a virus through the network. And just for example, just one camera being compromised and joined botnet, and they start asking its neighbors, hey, do you know, hey, I'm new mods node here. Do you know which is where is the latest configuration from our master? And the other botnet nodes will share the latest configuration to them. So it's there's no centralized server to distribute that. Everyone just sync by themselves, sync offline. So and the other thing is, we have experience of the centralized botnet. So you may want to ask, so as a security company, is there possible we can take down something, or we can fake some certificate? Oh, we can fake some config to tell the botnet, hey, how about you kill yourself? But it doesn't work because developers they use a private key. It's all the config are digitally signed. Only the person who holds the original private key can issue the commands to the whole botnet system. So which makes it's almost impossible for security researchers to hijack the botnet and tell it to stop. But things changed on 2023. So in 2023, there's a trigger because we monitor like there's a mysterious configuration update sent to the almost all the Mozi nodes on the August 21st, 2023. And the payload is a specialized controlled file signed with the original private key. And the execution of this payload is tell the Mozi node to, hey, stop execution, disable the SSH and telnet services, and the initial self-deletion. So, so we're just wondering how. So, because only the person who have access to the original code and the private key could have the authorize the cleanup. So there are lots of guessing around the world, but likely it's coordination between law enforcement and the security company. They taking down they arrest the developer, or the developer is acting under the legal pressure. So here's something about the industrial revolution of Mozi. I think it's around 2019 and 2020, during the pandemic, we noticed there's a new version of Mozi. This new version ditched the inefficient GAFGET. If you get familiar, it's a very classic botnet. It's not very efficient, but it's a classic one. And they adopt the Mirai attack framework. And Mirai is another most famous or infamous botnet in the IoT history. So basically, it has a built-in brute force dictionary. You can use that to brute force telnet login credentials, And there are a lot of copycats of the Mirai because the source code is already published. So people create a lot of variants, and you can even modelize, launch different kinds of DDoS attack. And that's where I think Moz became like it's kind of business, because it decouples the control layer, which is the P2P backbone, and from the business layer, which is attacking nodes. So it becomes a botnet as a service. So with those attack service, the operator could rent out the attack clusters to third-party criminals or script kid, so anyone who interested. So and I think this also it's a little bit of reliance secret of small botnet. So you can, as security companies, we can block attack servers. We can block the C2, just like we block our traditional C2 network. But the brain, the business part, the control part, the P2P network backbone remains hidden. So the P2P network just simply wait until it receives next signed config, and it can which point to another new target. Then can launch another round of attack. So I think here's the reality, because the undying echo. Because there's so why in 2020 after we've been through all this, we try to kill small nodes. We collaborate with like the government, try to take down botnet. Why we still see the most traffic in 2026? I think there are three major reasons. The first one is isolated Iceland, because there are a lot of nodes behind the strict firewalls. They never received the kill switch from 2023, so they just continue pause in the dark. And the second reason is supply chain route. As a security researcher from security company, we saw millions of old exploit traffic every single day, and surprisingly, some of them still works on specific devices. So there are millions of IoT devices from 2019 to 2022. They are still online, still unpatched, which become like a permanent soil for the infection. And the third reason, I think, is the most important one, because the Clone Wars, the new threat actors. Also the original developer has already been arrested or under control, whatever. But I think the source code has already been spread out. People are sharing the source code, making some change, and they started reusing this framework, change the keys, change the digital signature, and use Moz DNA for today's attack. But as a security company, we are like data driven. So with a huge amount of data, we choose Iceberg to help us to manage and help us to find those interesting, not only the significant, but also some hidden botnet behaviors. So I think in the foreseeable future, Moz will persist within the flows of network traffic and become like a constant white noise in the IoT digital age. Yeah, that's pretty much everything from our side. Any questions?
Oh, here.
Thank you for the sharing. I'm wondering, can you elaborate more how you use the public graph? How you just using the data structure, or you use any graph?
We actually heavily use PappGraph's engine. So PappGraph's engine give us a impression it can process a huge amount of data in a very, very fast speed. As I said, we have like trillions of bytes of data every day. Every day. If we want to track the trends, if we want to see in the past week what's this botnet trends, we need to process maybe 10 or 20 trillion bytes of logs. We need a powerful engine to help us to process it. We need to write some like ciphers or Gremlin query language, and we need to use this to filter the data or filter the island shape we want. So that's how we leverage the public graph.
So do you just use search, or you do any clustering or some?
The public graph backend is the Iceberg, is the buckets. Buckets, we store data in the Iceberg format, and public graph is like built up on that. Yes.
Thank you.
Any other questions?
Thanks for sharing. So this particular botnet, Mozi, what are your recommendations as as a cybersecurity company? What should consumers do of any size to protect against that?
Oh well, for first, this botnet Mozi, they have the brute force to try to log in the device. So my first recommendation is use more sophisticated password for your telnet login credential. There is always keep updating your firmware, try to patch the vulnerability, because we notice the threat actor behind the mods or the operator, they always try to adopt the newest or the latest exploit in the wild and try to leverage that to spread it. So as long as we keep up with the security patch, I think we'll be good. And I think for the traffic wise or the endpoint wise, I don't think the mods have lots of change in the behavior. So I think we have a lot of outstanding research. For example, like the 360 NetLab, they published 2 amazing technical research. It mentioned a lot of IOC of mods. We can use that as a reference to do some on-device detection.
Yeah. The other question that I have is about puppy graph. So in a landscape where there could be exploited or compromised hosts, how could the puppy graph, or are you guys like using puppy graph to improve observability? Like how does the puppy graph fit into the picture?
Yes. So I don't know if you're familiar with some like, for example, let's take an example. So we can find some specific patterns from the puppy graph results. That means some of the nodes in this pattern has been compromised. So puppy graph, we have a lot of like evidence. Sorry, I could not share it publicly, but trust me, there's a lot of ways with puppy graph, with graph search you can do to discover hidden stuff.
Is it like old school, so to speak, digital signature matching that puppy
No.
graph can help? Okay.
It's like from the graph relationship.
Okay. So more like theoretical computer science. Okay. Graph theory. Okay.
Any other questions? All right, thank you.
Yes. Recently, a lot of cybersecurity companies reach out to us because they have a lot of failed test to SQL product. I think the main reason is that for most industry, maybe 10 tables is good enough, but for cybersecurity, it's very common to have 1,000 tables. And currently, we already have several one in production who build a customer-facing agent system across thousands of tables. And let me explain what's the benefits and what's the reason of the failure of text to SQL. And we believe, let's look back to the history of big data platform. I think the first one is kind of MapReduce and Hadoop, and it's designed for software engineer because you can only write Java to write a job, and you need to spend hours to write a job and hours to run a job. And if you don't know Java or maybe Scala, you cannot handle it. So only software engineer can be benefited for it. And for phase 2, we believe Spark is a game changer because they talk with the people who are not software engineer but still want to do the data analysis. And they can still process the unlimited data, but at the same time, they design interface with Python, SQL, R for the non-engineer. And at the same time, they manage the tables and much faster than Hadoop. Since if you write the jobs only in half an hour, you don't want to wait for multiple hours about this. But we believe that for agents, there's something different because agent SQL, R, and Python are now designed for agents. And based on the collections feedbacks of our potential customer and also some in production one, they also share the experience why they failed with text to SQL. And I think 3 hard requirements for a successful agent system. One is that process unlimited data. This is straightforward because people already have unlimited data. And the second one is the sub-second. This is something new. Like I think Lakehouse also is a good player on this. Is because agent can write a job within 1 or 2 seconds, and you don't want to wait for 10 minutes or half an hour to wait for results. Then it's a kind of a freeze of agent system. And but before you don't care because the boss just like a data analysis. Please answer me this question, and the data analysis will come back, run a job, take a cup of coffee, and wait for the result, and come back to the boss. But now boss directly talk with agent, and the agent never stopped. And the third one, I think, is a kind of unique position for us because I think agent need an API embedded with ontology and semantic. And this is especially important when there are a lot of tables. So for example, we have a teacher table, we have student table, and also teacher salary. You can join all this table. Like you can join the student with salary table. And then, for example, Alice will have a 6,000 salary and no errors throughout. And at the same time, you can even join the student table and the teacher table. And then the ID can match, but you don't know what's the result of it. In this case, you have to have some harness about it. So we're trying to compare with ontology embedded or without ontology embedded called self-driving of cars and the trains. But of course, you can take Waymo now, but it's much harder than a self-driving of trains. We're trying to meet these 3 requirements. So for first is that we're trying to native sharding and shuffling and also feathery engine on Iceberg. Thanks to Iceberg is unlimited scalability, and our engine can also leverage it. And for sub-second performance, we focus on optimization for the complex query. Like you have 10 hop joins, or you have BFS. And in this case, usually most people don't optimize for it. But based on our feedback and the error logs our customers send to us, agents never care about the complexity. They can write as much as a complex query as they can. And by doing not except the optimization, we also do the scale out MPP and the wax-write evaluation to make it fast. The third one, what we do is that we just let the graph query language only can run when the query is aligned with the semantic and ontology. Otherwise, for example, if you have a edge between teacher and the salary, and then you can only generate a query from teacher to salary. Otherwise, it will just throw out an error, and we try to make the error message large language model readable. It will send back to large language model and generate a new query. Until you have a correct query can running, and you something like Rust, since like C++, you can compile the wrong code, and then you may have some race condition, but the Rust are trying to block on semantic check. We do similar thing, but a real semantic check for the semantics in real world. In this case, if you generate a query which is not aligned with the ontology, we will just throw out an error. And also, the query and the error message can be do the reinforcement learning to even have a more better accuracy, and then we can have less retry. And our architecture is that since no one wants to migrate their data, so we can just query on their existing data. And I think the most common data source for cybersecurity company is Iceberg and Lakehouse. I think is one of because the scalability, another is because of performance. And you can still use agent to generate like a single table or several tables query, but at the same time, when you have a complex query, you want to have a complex ontology, because the ontology is a graph, and we can just leverage it and have a reliable system in production. And this is how we do it, like a question coming in, and the agent will generate a graph query, and we will do the graph modeling to make tables to a knowledge graph. But you don't need to have a real knowledge graph. In our theory, you have tables, you have knowledge graph. And then we have a retry system, and we do the reasoning and the to calling. If to calling throw out an error, we will do the reasoning again. In this case, it's not just the wrong query will be throw out error. Even sometimes you generate a correct query, but take too long time. We still kill it and run a new query. Sometimes, actually a lot of times, it's just write a better graph query, and it's much faster than the first one, and then we can still have the real-time response. And by doing this, this is a real example, like how many electronic failure has Crusher CR 6000 has. We will let a large model agent to generate a pattern match and trying to match the graph schema. And then all the data are in Iceberg. And after that, we will throw out a result. Here, we just got the result because the query is kind of simple. It's the result is 70. Send back to large model, it will generate a human readable query in the final steps. And we also have some in product. Oh, this is maybe a big launch in big companies itself. It's I think 2 months later they will have launch in their own summit, and it's just kind of a with competitive product, and they can just answer different questions like which virtual machines are exposed to public IPs without any security group protection, without any security group protection, while also running software that contains vulnerability XYZ. So you know that is even for human being, it's not too easy to read this query. But the lucky thing is that it's really in production and it's a kind of a ad hoc query, but it's just to give you the correct answer. And something more recent, you can see the page is very ugly because I just do it today, because one of our users reached out to us. They do something for open cloud observability, because the open cloud is just generating log, keep generating the log, and no one know what happened. Not to mention about the security. Even it's a spend token, do the payment, no one know what happened. But actually, it's just a trace store. You can just keep streaming the trace into Iceberg, and then you can answer some question like what happened end to end, and give you some visualization, and also why did this run fail, and also why did it cause the latency spike. Like most important, where is your token gone, and then of course what fix prevent recurrency. And this is a pure advertisement. Is about which we have which customer. You can see that most of customers have super big data. I think this is a big differentiator from us and any other graph database. Yeah, and any questions? Yeah.
Please.
Thank you. So just trying to understand like puppy graph, bear with me, I'm not like familiar with the idea of puppy graph, but at a very high level, it sounds like it can act as a knowledge graph for LLMs as well, or agentic AI.
Yes. I think since a lot of knowledge graph guys talk about why knowledge graph is important in AI, I totally agree with them. But before I joined Google, I work at a graph database company called the Tiger Graph. It's super hard to let an enterprise to adopt a graph technology because no one wants to put all their data lake into a knowledge graph. It's almost impossible. And after I joined Google, based on the scalability and the data size, and I work at a SQL query engine team. It just query all the data across Google without moving it. And I feel, oh, this is very important. And then I think most people want a graph on their data rather than bring all the data into a graph. So that's why we design our product and trying to give an interface of a data lake, trying to give a graph interface for everybody's data lake. And then you can run it on scale, and also is much easier to onboard.
Thank you.
Great. Thanks for the sharing. I want to know more about when you talk about the ontology enforce. Seems your example is only teacher have the salary. So if I join salary with the student, they will have some error. Or
yeah. So interesting part is that for SQL, you can see this table. If you draw a student table with a salary table, and the student ID actually can match the teacher ID, and then it won't throw out an error if you just generate a SQL.
I just wondering, these logics come from where? For example, it's just come from the language model's common sense, or actually we can set some rule. But because sometimes students do have the salary, right? Because they can add as a TA. So I'm wondering where is the logic we can set those rules that when violate these rules and give us some errors. Where are those logic?
Yeah, sure. In this example, you can see there are 3 tables. For agent, if they don't have additional context and knowledge, they just join randomly. But if you can build a graph on top of it, you will have, for example, this 3 table, you can only see that the teacher ID connected to salary table through teacher ID. And at the same time, if you want to have a relation between teacher ID and the student ID, usually there will be another many-to-many tables called the teacher teach student. And then in that table, there will be a teacher ID and the student ID. In this case, we can easily define which table is a type of nodes, which table is a type of edge. And after that, physically, there are still tables, but logically is a graph. And then we can just query along with it because you already have the knowledge graph, you have the graph schema. And then all the query must be along with the edge, which means you limited the possibility which table can be joined with which table on which column. And currently we see some, for example, Snowflake trying to do some called semantic standard. It seems that they're trying to do the prompt engineer and let the large model know that this column can only join with this column. But first, it's very hard to do the prompt engineer at the beginning, is a human labor. But at the same time, you cannot rely on a large model. Sometimes they just reply, I understood, but when they really try generating SQL, is just generated the wrong one. But because SQL query engine itself won't throw out an error, and then you cannot control the error rate. And a common conclusion is that is a feedback from a lot of customers. When you have more tables, the text to SQL rate will be error rate will be higher. So if it's just for some traditional company, enterprise, maybe only several tables, it's not a big problem. But for a company who have a lot of tables, especially for cybersecurity company, and it's happen a lot. It barely have anything in production. That's why a lot of them reach out to us and teach, oh, this is the situation, and we want to have knowledge graph, but it is very hard to build a knowledge graph from zero based on the existing data lake. and we try and kind of give them a shortcut to have a knowledge graph immediately. Yeah. Any other questions? Please.
So this like API like value proposition that you guys have, is that like equivalent to like MCP? I mean, could that be replaced by MCP, or it's just like on intentionally an API?
Oh, it's MCP.
Oh, it's an
but after you send the request to MCP and when public graph is running, it will first check if the query. You can see that, for example, this is a real query. All the graph query are pattern match, graph pattern match. In this case, whether the edge exists or not must be aligned with the graph schema, and we can check it first. And then for the engine semantic check stage, we will throw out an error, which means this is auto for large model to make sure you feel safe. Yeah. No, please.
So my question is more towards the LLM agent. So how effectively LLMs can translate a natural language into a graph query? So do you see any challenges of LLMs not generating the right graph query for a natural language?
Oh, actually we did this on purpose because we're using Cypher, which is a graph database Neo4j designed and is existing for many years. So there are a lot of public data set can be trained by large model. Based on our current experience, is pretty good. But if some others like recently there is a standard called GQL, is a graph query language, and is a ISO standard. Actually, I'm in the committee, but the bad luck for the standard is that after it's launched, ChatGPT also launched. And no one write real query by themselves. Everybody is just generating it. And for GQL, there are not enough public data sets, and it's a big problem. And maybe it's a dead standard. And hopefully will be more data set. But based on the reality, we just pick up Cypher because a lot of code on GitHub and trained by large model, so we can generate it efficiently.
Just an extension of that is sometimes one query might not be enough, right? There could be multiple subqueries that are necessary, and aggregation of that subqueries could be the response that. So how do you deal with that complexity of?
Oh yes, this is a pretty critical since actually at the beginning of last year, and AMD reached out to us for this project. And at that time, most of people just do RAG, and it's kind of one short text to SQL. And the lucky thing is that one of my roommates work at a large model company, and he told me that only agent can make it work. You shouldn't follow some other player like text SQL or graph RAG. Just do the one shot, and then we do the agentic system. In this case, if the query is complicated, and you can just do the prompt engineer and let the large model know that you can divide it into subtasks. And each task may be a query, maybe two. And after that, is a step-by-step, depending on the previous result. And then you can have a better one. And at the same time, we're trying to just print all the steps when you do the stuff. And also we do some auto, we have open source framework, which is preload some prompt engineer there, and then to try to make sure it works well. And also, because on each step, if you throw out an arrow, it can look back to see, oh, this is wrong. But if it's just a pure text to SQL one, sometimes it's just generate a wrong SQL, you still give your result. And the agent won't know that, oh, this is wrong, and you just continue. And when you really realize it's wrong, you need to trace back for several steps earlier, and which is hard. So we're trying to make each step throughout a meaningful error message. But of course, it's still not a perfect one. But based on the feedback, usually before customers sign contracts with us, they will let their stakeholder to ask us some random question or give them some random task. Usually the stakeholder is happy about that. So and also because we are working with them and trying to improve the framework, and we are pretty confident about make this kind of agent system in production.
Thank you.
Hi, thank you again for the talk. On one of your other slides, you had something similar to this where the LLM would take the query and then munch it out. And you said sometimes that the query itself that it generated was bad, and so it would just reset and do another query, right?
Yeah.
I was wondering if the LLM or LLM agents ever took a query and decided that the schema that you have for the graph was inefficient for being fast and would just rewrite, maybe fan out the whole graph entirely just so that I could do the query much faster. Have you ever seen that behavior?
Yes, sometimes you generate a wrong, since we have a hard timeout for the example 30 seconds, and if you still haven't got an answer, we'll kill it and generate a new query. But sometimes it always generates the slow query. But in this case, there are two possibilities. One is that just no good query. Another is that the query itself just too resource consuming and is impossible. And usually at that time, human being will give up. And that's the last chance we can save this agentic system. And then because they won't ask this question, just give it up. And this is the last shot.
So sometimes the LLM will try to do a restructure on the graph, like maybe say, oh, this should be a label, that way I can run the query more efficiently?
Yes. And also, we won't have a limited retry. We will have some certain stops to give a break. Yeah.
Okay, awesome. Thank you so much.
Thank you. Oh.
And excuse, your cloud trace AI. I'm curious. Is that a platform to? Is there an API to use, or you will open source later?
Oh, yeah. This is a YC company who is just building this project.
Oh, so it's not.
Is it?
Yeah. So it's not your product.
It's not my product, but they just reach out to us like if we can just put a logo here. So I try to do a favor for them. Yeah.
I'm curious about this. Okay.
Yeah. Oh, please.
Hi, I'm curious if the agents can kind of build internal context over time as you ask them questions. Like if you ask one question about the data and it needs to make some relationships, and then you come back and ask, another question later building on that, does it have that context of how it answered that first question and can maybe do the second question a little bit faster? Or does it kind of not have that context of the previous actions that were taken on it?
Oh, our next release, okay? Since a lot of people complain that we need to rebuild the ontology graph first, so we have something like you can just connect to your Iceberg catalog and list all the tables, and then you can ask a question. And then when they are not sure whether these two tables can be joined, and then they will ask you, I'm trying to connect these two. Please approve or reject. And by doing this, you can just ask a question and then build the ontology through the chatbot. Yeah.
Thank you.
Any other questions? All right, that concludes. Yeah.
No, thank you. Yeah.
And that concludes all the talks, and we still have desserts and drinks and food, and our caterer actually will bring some takeout box. So if you want to stay for a little bit, they can pack it for you, and so feel free to take it home and then take multiple of them.